Let's talk about quantum mechanics.
Okay guys, brace yourselves. It's time to dive into the true weirdness of quantum mechanics. And I'm going to start by dispelling a myth that your high school teacher probably started. You were probably once told that there was something called a wave-particle duality, where things like atoms and electrons, they have a duality of nature where sometimes they behave like a particle and sometimes they behave like a wave. Well, don't believe it. It's not true, and it's a horrible way to understand what's actually going on in the world around you. So here's the thing. Particles don't move. Shocker, particles don't move, okay? If you can just accept that one fact, then you don't have to worry about this wave-particle duality business anymore. Well, since we were kids, we always believed that if I push a ball, it's going to roll, it's going to move from one place to another, and it's going to pass through all the points in between. That's the way we've come to see the world. Objects or particles move from one place to another. But unfortunately, that's not what happens in quantum mechanics. As we get to the microscopic realm, we find out that particles really aren't tiny little objects. What we attribute to a particle are the properties associated with it. It has a color, or it has a size, or it has a mass, or it has a momentum. And in quantum mechanics, those properties we call quantum. And each object, whether it's an electron, or a proton, or a neutron, or a neutrino, has associated with it a quantum of something. For instance, an electron has mass, it has charge, and it has momentum. Okay? It also has something called spin. So each of the particles each of the things that we believe to have been particles at some point, actually are just things that we can measure. And these things that we can measure come together as a group, and they propagate. And they can get discovered. But they're not a particle that moves from one place to another. These properties are all associated with a wave that sloshes around in space. It can reflect, it can split, it can combine, it can diffract, it can do all the things we've seen waves do in our bathtub or at the beach. So when we talk about the world of quantum mechanics, we're not going to think about particles moving, we're just going to think about waves. And this is how we do it. An electron is a wave. And this wave has a peak. That peak tells us where we're likely to discover the electron, or in other words, where we're likely to measure one of its properties. We could discover its mass by bouncing something off of it and seeing how much it recoils. We could discover its charge by seeing how it interacts with the magnetic field. So this wave, where it's peaked, tells us where we're likely to find the electron, but we don't actually know. There's a probabilistic nature associated with it. Now, one of the things that we could do to sort of illustrate the wave nature of electrons or other microscopic particles is actually try to narrow down their position and see what happens. So I'm going to feed a beam of atoms out of a little gun here and shoot them, and I'm going to look at them under a microscope and try and count these atoms and prove that there actually are particles. So what happens is my microscope focuses light on this particle, and I have a range of incident angles of light. When that light hits that particle, it's going to deflect it. But I don't know what angle of light actually, what angle light was coming at when it hit that particle. So it's going to deflect into a range of different directions. Each of these directions has a vector momentum associated with it. So the more tightly I focus that light ray, using more and more high angle light, the more tightly I focus that, the wider the spread of momentum there is. So to really precisely locate something, I have to really screw up its momentum. That's the uncertainty principle. You can know something's position very, very well, but its momentum becomes undefined. A simple example. It's a little bit easier if we discuss something that's more familiar to you. There's really two ways, just like position and momentum are two different ways of describing an electron. Emotion and behavior are two different ways of describing people, or even things that happen. For instance, my friend comes back from a game, and I say, "How did it go?" And he said, "We won!" And his girlfriend says, "It was so fun!" Okay, so he's describing the event, and she's describing the emotion behind it. It's actually really interesting to think about how psychologists actually do their work. Let's say we have a case. This person is a little bit agitated. He's aggressive sometimes, easily angered. The person's a little bit OCD. And here are all these sets of behaviors, and he's also very withdrawn. These behaviors seem very unrelated. Is he depressed? Is he OCD? What's wrong with this guy? When it turns out, all these behaviors could be due to a single thing, anxiety. So here in behavior space, I have a whole bunch of different things that are going on. It's a pattern that I have to match. But if I just look at the emotion space, it's due to a single emotion. And if I was to ask someone, what single property defines all these behaviors, you would say, oh, obviously it's its wavelength or its frequency. So here we have what would be the analog of position space in quantum mechanics, and here we have the analog of what would be momentum space. When there's a variety of behaviors with a well-defined relationship, we actually can resolve a single emotion. On the other hand, if we look at a single event that happened in time, oh my gosh, I just got dumped. And there were some behaviors and events associated with me getting dumped, like a text message. If we try to look into that and see, well, what were the emotions behind that dumping? We don't have a lot of insight into the emotion, unfortunately. So on the other hand, if I was looking at a pattern of behavior over time, I could really see that the emotion was dissatisfaction, which may have something to do either with my car, my physique, or my body odor. As a random, non-specific example. So this experiment is called matter interference. I have a beam of atoms I'm going to put into a laser chamber. I'm going to shine a laser on that beam such that about half the time, atoms will absorb or scatter the light and get deflected. These atoms are going to head off in this direction now. But some of the atoms that don't absorb or deflect the light will head off. Now, the wave of the matter is influenced by the wave of light such that it splits. You could think of if you had an obstacle here that would cause a wave to split into two different paths. In other words, half the time the atom will deflect and half the time it won't, but that atom doesn't know whether it deflected or not. It's just a probabilistic thing as to whether the properties of that atom, its momentum and its charge, will get discovered here or get discovered here. And it's an interesting experiment to do, to put a detector here and find that you don't have half atoms here, and you don't have half atoms here. In either case, you always get the whole atom. You just don't know which arm it's going to be in. Well, to combine these waves, I'm going to give it a full pulse. And this full pulse will cause the entire beam to deflect. Now these beams are going to recombine. What's going to happen? Well, just like waves interfering on the shore, you'll get a pattern. What is this pattern? Well, it's a pattern of where you're likely to find atoms and where you're not. So if I view on a screen here a bunch of electrons coming in, these electrons will have locations where you'll see a lot of brightness on the screen and locations where you won't see a lot of brightness. At these locations, one atom wave or one electron wave is out of phase with the other, and the two are canceling each other. This would be like if you walked into a wall, half of you bounced off and half of you went through the wall, and later on you ran into yourself, and what happened is that each time you did that, you randomly ended up at a different location in the hallway, which is what's actually happening. So these atoms are not actually splitting. Their waves are splitting, and their waves are propagating. Each of those waves has associated with it a particular quantum. In this case, if it's electrons, it's going to be the electron's momentum, its charge, and its spin. Okay? And these things can then be discovered or measured at any point we put a detector. So if we block one of these arms, this interference pattern will go away because the wave can't interfere with itself. So you can do that one atom at a time. The first atom comes through, maybe it lands here, maybe the next one lands here, maybe the next one lands here. But each individual atom, one at a time, will experience diffraction by itself. Very cool. Next time, I'm going to teach you guys about LEDs, which is quantum mechanics actually operating in your everyday life, from your smartphone to your television, your car. LEDs are revolutionizing our world, and they're based on quantum mechanics. We're going to learn about solid-state physics, and it's going to be a lot of fun. See you next time.